There's an old joke about particle physics. Don't trust atoms. They make up everything. While that's obviously not totally accurate, much of the things we encounter with on a daily basis is formed of atoms. Thus it seems to reason that we must all learn about them. And we're taught in school that atoms are made up of some mix of protons, neutrons, and electrons. The simplest atom has only one proton and one electron. This is hydrogen. Yet it turns out that there is an element even simpler than hydrogen out there. It's called muonium, and it might help scientists unravel the deepest secrets of physics. Muonium is named after a particle known as a muon. So let's start with an explanation of what it is. It's essentially a particle that has the same negative electric charge as an electron. Yet, there are two significant distinctions between them. First, a muon is around 200 times more massive than an electron, yet it is only about 9 times lighter than a proton. Second, it is unstable. It will spontaneously decay after around 2 millionths of a second, leaving behind one electron and other strange subatomic particles. The 2 millionths of a second are, of course, incomprehensibly short to us, yet, it is long enough for muons to interact with other particles. Not just that, but to have connections with them. This involves creating anything that resembles a hydrogen atom. This, however, is illogical. If a muon is negatively charged and hydrogen is supposed to have a positively charged proton in its center, how is muonium, another kind of hydrogen? It's because a conventional muonium atom does not include a muon. It's crazy, I know. It instead employs an antimuon. Yeah, we are dealing with an atom that contains some antimatter. While images of matter, antimatter, and explosions may have flashed through your mind, antimatter is simply a different matter. Every subatomic particle has anti-counterpart with the same mass but the opposing electric charge. An antimuon has the same mass and decays in the same length of time as a muon, but it has a positive charge rather than a negative one. And here's the key point. The strength of that positive charge is exactly the same as the positive charge of a proton. So if a regular old electron is in orbit around an antimuon, that is a muonium atom. Those things don't violate each other because they're not each other's matter-antimatter counterpart. And when it comes to chemistry, the difference in mass between a proton and an antimuon doesn't matter nearly as much as their identical electric charges do. So an atom of muonium, ignoring its super short lifespan, acts as a chemical in almost the exact same way that a proton-based hydrogen atom does. This is why some scientists consider muonium to be the lightest form of hydrogen. And just like other forms of hydrogen, like deuterium and tritium, chemists gave muonium an honorary chemical symbol, a mu. Now, if you prefer to think about muonium as its own element and not like a quirky hydrogen, that could make muonium the simplest element in the universe. Just like muons, antimuons are fundamental. They are as simple as a single subatomic particle can get. Meanwhile, an individual proton is complicated. It's not fundamental. Each one is made of smaller particles called quarks. So even if the simplest hydrogen atom only has one proton and one electron, muonium is even simpler. These days, antimuons are actually fairly easy to create in particle accelerators. Although they come out traveling pretty quickly. So making muonium requires taking a concentrated beam chock full of antimuons and then slowing them down. This can be done by literally putting aluminum or gold foil in the beam's path, which slows the antimuons down by making them bump into electrons and the like. When they get nice and slow, the old adage of opposites attract kicks in. The positively charged antimuons can peel off some of the negatively charged electrons orbiting other atoms to make a bunch of muonium. Now, physicists are not making all of these exotic atoms just for fun. They want to make muonium because it lets them use experimental techniques from the well-developed field of atomic physics to study our murky subatomic reality. For instance, each atom has a unique sequence of colors that it emits and absorbs. It's called a spectrum, and it basically is a barcode that lets scientists learn more about the subatomic structure and properties of a given atom. Muonium has its own spectrum, too, which is easier to calculate because the atom is simpler. So scientists can study the spectrum in exquisitely precise detail and use that to test what physics says muon should look and act like. And since those theories tend to describe how other particles are supposed to act, it turns into a test bed for all of particle physics. But muonium might even help answer questions about a phenomenon that's a little more tangible to human minds: gravity. Specifically, does gravity pull on antimatter the way it pulls on regular matter? No one knows this because no one's made enough antimatter to properly weigh it. But muonium may be the perfect solution. Not only is muonium relatively easy to make, the atom as a whole is electrically neutral, and that means it will be easier for scientists to screen out any effects caused by the electromagnetic force and focus solely on how gravity is acting. And because we're in the antimatter game, antimuonium is also a thing. Instead of an antimuon forming a bond with a regular electron, this involves a negatively charged regular muon combining with a positively charged anti-electron. So if scientists ever spot atoms of muonium and antimuonium falling in different ways under the same conditions, either faster, slower, or even in different directions, that will be a clear sign that there's some new unexplained physics going on. Meaning that, yes, the atom that breaks all the rules might break one of the biggest rules in the universe and literally fall upwards. We may never see muonium get its own box on the periodic table or taught to the next generation of elementary school students, but it could turn out to be one of the most important atoms in our quest to understand reality. Atoms are bizarre quantum objects that make the world go round but also break the rules of classical mechanics and probability.